Hi everybody, and welcome to today's lecture on electric circuits, something that's part of our everyday lives, but we probably don't really understand much about what's really going on in an electric circuit. Okay, first of all, what is an electric circuit? Well, basically it's anything that uses or collects or stores electrical energy. So plugging your toaster into the wall is creating an electrical circuit. All these different things will create all kinds of electrical circuits. Now, most electrical circuits can be composed of a lot of these components. There's resistors and capacitors and diodes and LEDs, all these different things like that. But to break it down to the simplest type of circuit, there's only really three main components to what we're going to call a simple basic circuit. They are the current, the voltage, and the resistance. Now, electric circuits relate to both the idea of electrical energy and electrical power. But in turn, we're going to see how we can also relate electrical energy and power to mechanical energy and power. Because in the end, a lot of times we plug things in order to do some sort of mechanical work. For example, a blender is plugged in to do some sort of work on whatever you put in it. So to begin with, let's talk about current, which is given by the symbol uppercase I. Current is defined as the rate at which charge flows. And now, remember that whole term rate. Rate means something over time. And when we learn electrostatics, we use the letter Q for charge. And then this is the actual electricity that's moving through the circuit. Now, this is also a very, very big difference between static electricity and current electricity. Static electricity, again, only flows on the surface of an object, but current electricity actually moves through things, making it a very different type of electricity. So what we're dealing with here is actual moving charge, okay, as it travels from one place to another. And by the definition, current being the rate at which charge flows, I must be Q divided by T, the rate of charge. And the unit of current is a capital A, which stands for the amp or ampere, named after Jean Ampere, in case you're interested. Now, when we often talk about the flow of current, we talk about, of course, if you have a battery that has a positive and negative end, when you hook it up, your electricity is seen as flowing from the positive to the negative. That sort of high to low idea in nature, positive being high, negative being low. But let's think about that for a second. If current is said to begin on the positive and go to the negative, in other words, flow high to low. Well, if current is moving charge, well, if we remember from electrostatics, it's the electrons that are really in motion. Okay, so for current to move from positive to negative, if we were to think about the flow of an electron, it wouldn't naturally flow from a positive to negative because it would be repelled by the negative and attracted to the positive. So in reality, what's really going on is that although we say current flows from positive to negative, it actually doesn't. It's the other way around. Now that's the difference between something that is called conventional current versus something called true current. Well, why the difference? Turns out, again, true current flows from negative to positive. That's due to our old friend Ben Franklin. Remember, he came up with the terms positive and negative, and in his ideas of electricity, he thought, well, nature tends to go from high to low, so positive should be the high and negative should be the low. Now, this is before really understanding the way charges worked. So here's the interesting thing. Even though it's not physically right, the world operates on the principle of conventional current. So we're going to operate the same way. We're going to stick with positive and negative. In other words, we're going to stick with Ben Franklin. Now, so if current is the rate at which charge flows, and let's say we have 5 microcoulombs of current traveling every 10 microseconds through our wire here, and the idea is, well, how much actual current does that give you? Well, current is the rate of flow of charge, Q over T, Micro is 10 to the minus 6. So we've got 5 times 10 to the minus 6 coulombs over 10 times 10 to the minus 6 seconds, which gives you 0.5 coulombs per second, or 0.5 amps of current. Coulomb per second and an amp are the same thing. Okay. Now, is that a lot of current? No, not really. I mean, you couldn't operate a hairdryer or anything with it. But interestingly enough, that is actually enough current to actually kill you. It doesn't take a whole lot of current, it turns out, to actually interrupt the beating of your heart, essentially. Your heart is basically operating on electrical impulses. And because current has the ability to travel through things, it can travel through our bodies, which makes electrical current so much more dangerous than static electricity. Remember how we talked about in electrostatics that you're safe in your car if lightning hits it because the car is made of metal and all the charge flows on the outside of the metal. However, if you were in your car and a power line fell and hit your car, that current would enter inside the car. It would come through the metal and into you. Now think about this. A hairdryer, for example, operates maybe around 8 amps of current. Okay, so that's a lot of current, which was why they put those warning stickers on hairdryers about the electricity with them. So always be careful around current electricity. It is very, very dangerous. Second component, resistance, given conveniently by a capital R. Now, the way to talk about resistance is think about it like a form of electrical friction. Resistance is anything that slows down the flow of current. In addition, one of the things that resistance creates is heat. So it does act a little bit like the idea of friction. And the unit of resistance is the Greek letter omega, but it's called the ohm. So resistance is measured in ohms. Now, what makes up the resistance of anything electrically? Well, 4 different things. First of all is the length of the resistor. Now, we're going to talk about wires here, for example, because that's usually what electricity runs through predominantly is wires to get from one place to another. What can happen in a wire? Well, a wire, which is a solid, is of course made up of atoms that are inside of it. And those atoms actually are not stationary, they vibrate slightly. So anytime charge is trying to sort of move through here, those vibrations kind of help slow that motion as it goes along. So if we think about the idea of length, if I have a short wire and I have a very long wire, well, there's going to be a lot more resistance through that long wire than through the short wire because it's got to travel through more material. So basically what we're saying is that as length increases, resistance increases. And it turns out that they are directly proportional to each other. So again, what does that mean? Well, that means if I double the length, I double the resistance, directly proportional. So that's the first thing that affects your resistance, particularly in a wire. The second thing is called the cross-sectional area. And now what do I mean by that? Well, when you look at a wire generally, of course, has a circular shape. And the cross-sectional area is right here, the shape of sort of the opening, if you want to look at it that way. So, if you had 2 wires, one that looked like this, and another one the same length but looked like this, which one would resist more? Now, I know some people's immediate reaction thinks the bigger one, the fatter one, because there would be more material. But if you think about it, having a much larger area allows more charge to sort of come in together through that opening. Okay? Think about it like a water pipe. Okay? The bigger the pipe, more water can flow through it. So it turns out that as area goes up, resistance actually goes down. And this relationship is inversely proportional. So what does that mean? Well, that means that if I double the area, I inverted or cut the resistance in half, inversely proportional. The third, and probably one of the most important things that affects resistance, is its material. And that should be kind of obvious. Copper is a very good conductor of electricity, has low resistance. It's used in a lot of wiring. Gold is even better. Um, Other materials, of course, do not conduct electricity very well and have a high resistance. So material is a very, very big deal. And the fourth one is actually temperature. One of the reasons they keep a lot of computer systems and things like that in cold rooms, because as temperature goes up, so does the resistance. So temperature is also one of those things. Now, how do they all fit together? Well, there's an actual equation for resistance. R, resistance, equals rho, that's the Greek letter rho, times length all divided by area. And again, remember, resistance is measured in ohms, with that capital omega being the symbol. Now that rho is where the materials come in. Rho is called the resistivity. And basically there's a table of them. There's a chart of all different resistivities of materials. So it's just something that if it's copper, it has a certain value, a constant value. If it's gold, it has a certain constant value. If it's tungsten, it has a certain constant value. And the unit of resistivity is the ohm meter. So let's look at an example. I want to determine the resistance of a 10-meter long copper wire. Copper's resistivity, if we were to look it up, is 1.7 times 10 to the minus 8 ohm meters with a cross-sectional radius of 2 millimeters. Now, radius, why did I give you that? Well, again, resistance is given by rho, L, all divided by A, area. Now, if we consider, again, the area of the opening of a wire, it's a circle. So the area of a circle is pi r squared. Okay, so that's why you're given the radius. Now, if the radius is 2 millimeters, we've got to convert that to 0.002 meters. Got to be in standard units, right? So we have our resistivity, 1.7 times 10 to the minus 8, 10 meters, it's a good long wire, all over on the bottom, pi times 0.002 squared. Only that 0.002 is actually squared. And that gives a resistance of 0.014 ohms, okay, which is a very low resistance number. And again, that's why copper is often used as a conductor or in a lot of wiring, because it has a very low natural resistance, even over a 10-meter length, which is a good long length. That's basically how we determine resistance. Now, we can actually divide up resistance, though, into 4 very specific categories or types of resistances. The first type is called a conductor. Now, by that name, it means anything that easily allows the flow of a current. Okay, so good conductors, your metals, things like that, they easily allow current flow. Now, the sort of opposite of that is an insulator. An insulator is designed to restrict the flow of current. Okay, so this is where rubber comes in, which is why they surround these wires with rubber to protect you from, so you can handle them without any of the current flowing through the rubber to you, because it restricts that flow. Wood, air, things like that, those are all good insulators. Third category, relatively new, and by relatively new I'm talking about 60 years, is something called a semiconductor. And a semiconductor is something that very much regulates the flow of current. Where you find semiconductors is actually in computer chips. The discovery of the semiconductor was really what allowed computers to go from, if you had a calculator, it would fill an entire room with its components, to these tiny little things that we have now. So semiconductors are very important in terms of computing. And the other one, also relatively new, is called a superconductor. Now, a superconductor is a very interesting thing because it has actually no electrical resistance, okay, none at all. And it turns out in order to get superconductors to exist, well, again, you can use a regular conductor. And because that regular conductor has those atoms in there that sort of interfere with that motion, you again get that kind of resistance that's inside here. But if you can cool that conductor down, and if you can cool it all the way down to a temperature of 7 degrees Kelvin, okay, now that's 7 degrees above something called absolute zero, okay, which is supposed to be the coldest temperature you could possibly reach. At absolute zero, all atomic motion stops. Okay, all atomic motion stops at absolute zero. So now we're just talking about being 7 degrees above that. Well, that slows those atoms down enough so that when anything electrical wants to move through there, it just goes through without any air interference at all. Okay, but you have to be at 7 degrees Kelvin. Not an easy thing to do, right? There are some materials that can superconduct at higher temperatures, but they're expensive, so don't count on your houses being wired in superconductors anytime soon. Be nice though. Now, interestingly enough, anything that is actually an insulator with enough electricity can become a conductor. Okay, but it takes an enormous amount of electricity to do that. Here's an example of something that would normally be an insulator. Wood is not a good conductor of electricity, but with enough voltage across the wires, with enough thing called potential difference across the wire, it has the ability to push charge even through something that is a poor conductor, is more of an insulator. So this tree branch landed on two wires that have a difference in their voltage. So watch what happens as the current tries to connect from one wire to the other. It's actually making that noise. Pretty neat, wasn't that? Okay, so the last part of a basic circuit is called the voltage, symbolized with a capital V, conveniently. Um, and one of the things to talk about is something called an EMF, an electromotive force. Now, this is any transformation of non-electrical energy into electricity that allows you to move it through a circuit. So, for example, the most common type of EMF we deal with every day is a battery. A battery takes chemical energy and converts it into electrical energy. And the more what you call potential difference, the more voltage you have, the more force you have to push electricity through the circuit. Okay, and that's the big thing. The EMF creates something called a potential difference. It creates that high and low, and then is able to force the charge from the high potential point down to the low, from the positive to the negative. So the greater the voltage, the more push it has and the more current it can actually drive through any particular resistance. A little bit of a confusing idea, but again, that's why a 6-volt battery can push a lot more current than a 1.5-volt battery. It has literally the ability to push harder. So when you think about voltage, think of it as the thing that is driving the current, the thing that is actually moving the current or pushing the current from one place to another. Voltage is conveniently measured in also capital V, volts. So V is measured in V. A little strange for physics because usually we don't like to do that, but in this case they actually do. The term voltage or volts comes after, named after Alessandro Volta. He was the inventor of the battery actually. It was actually called the voltaic pile back when he invented it. Okay, so that's an introduction to the three basic parts of what we're going to later call a simple circuit. First of all, again, you have the current, which is the actual moving charge through the circuit, defined as the rate of flow of charge. Again, current can move through something, unlike static electricity that moves on the surface of something, making current much more dangerous. The resistance, anything that resists the flow of that current, and we saw that resistance was based on length, to which is directly proportional, cross-sectional area, which is inversely proportional, the materials, and the temperature. And then finally, this thing called voltage, which is what really drives the electricity, the mover of the charge itself, from what we're going to call positive to negative. Next time we'll look at how all three of these really relate together in terms of a simple circuit and how they relate to each other. So see you next time.